Breaking strength of a cable lifting a box. 20 kilogram box is being lifted by a cable that will break if the tension is more than 500 newtons. What is the greatest upward acceleration that can be imparted to the box? Step 1. Nothing different here. Draw a free body diagram. This is more of a force diagram, so remember, a free body diagram is just going to have the singular dot, and then you're drawing it. So we have the tension going up, and we have the weight going down. Our net acceleration is upwards, so that tells us our tension has to be more than the weight. Step 2, use the free body diagram to write Newton's second law equation. Net force equals mass times acceleration. Ft minus mg equals mass times acceleration. Positive adding the negative equals mass times acceleration. Note the force that is in the same direction as the acceleration is positive, and the force that opposes acceleration is negative. Right? It's kind of like a tug of war. Step 3, solve for the unknown, which in this case is acceleration. Plugging in these numbers, substituting in our numbers, we get acceleration equals 5 meters.
5? Plug in those numbers yourself. See if you get 10 meters per second squared.
Don't forget your units. Scale reading on an elevator. 50 kilogram student in an elevator that is moving upwards but slowing down at a rate of 2 meters per second squared. So we're moving up, yet we're slowing down. So what direction is our net acceleration going to be? Opposite, right? Because if our velocity is in one direction and our acceleration is in the opposite direction, we're slowing down. If the student is standing on a scale, what does that scale read? Step 1, what? Oh, misconception. Scale measures weight, so the answer is just mass times gravity. Next question, move on. No! Nothing in the universe measures the weight force. Scale is a surface, so a scale measures the normal force it exerts. So you press down on the scale, and the scale is pushing back. If it's a spring scale, you press down, and then the spring is pushing back by some amount. So that's how a scale works. So the reason why your weight is going to apparently change in an elevator is because if you are moving upwards, then the net force, which is also upwards, is going to have a different reading than if you are just stationary on the ground. Draw the forces. Since the elevator is moving up but slowing down, the elevator's acceleration is downward. So which vector is going to be larger? The weight is going to be larger than the normal force. Net acceleration downwards. Step 2, free body diagram to write Newton's second law equation. Weight force is positive since it points in the same direction as acceleration. Normal force is negative because it points opposite the acceleration. That is like super confusing to me. And this is where that first method of problem solving, I think, comes into play, and it does a little bit clearer of a job. So I'm going to go through that with this problem at the end. Step 3, solve for the unknown. So we have mg minus fn equals ma. This minus fn equals this, and we're solving for the normal force, which will give us the scale reading. And we get 400. All right. I'm going to start with the free body diagram, and then go to Newton's second law equation and creating my own equation. My net force equals the stuff that makes it go minus the stuff that holds it back. This way you don't have to think, is my acceleration in the same direction as my velocity? You don't have to worry about any of that. Equals our net acceleration. So what's making it go in this case? The weight, right? The weight of this whole thing is going down. So that's the direction we're going. So weight is making it go, what's holding it back? That normal force. Equals mass times net acceleration. And then you can plug in your numbers here. And I'm not going to go through all that because you're smart enough to do it. So again, either method works for you. This one works for me because I like it a little bit simpler. And to me, this is simple. I don't have to think. Other one works just fine too. Wait a minute. 400 newtons. 50 kilogram student. Wait a minute. Sometimes I feel lighter than I normally feel, and sometimes I feel heavier in an elevator than I normally feel. That's because you have never felt your own weight in your lifetime. What you're actually feeling is the normal force acting on you at all times. We can't feel ourselves pushing down, but we can feel the earth pushing up back on us. Pretty crazy, I think. But that is why I enjoy physics. Just weird things like that make you stop to think. So the student in this situation feels like he is only 400 newtons, but what he is used to feeling is 500 newtons. So to him, he is feeling lighter, right? Because there's less of a normal force acting on him. Since he only feels 400 newtons instead of 500 newtons, he feels 20% lighter than he's used to. This is because the elevator's acceleration is 2 meters per second squared, which is 20% of gravity. If the elevator had an upward acceleration of 2 meters per second squared, the student's going to feel 600 newtons. So it's going to feel heavier. We also get this on the roller coaster. That's why I like doing field trip to the theme park. On the roller coaster, when we are coming over the edge and we get that heavy feeling, it's a heavy feeling. We're not actually heavier, but what we're getting is more of a normal force than what we're used to. Mario, feeling heavy, feeling normal. And now he's lighter as the elevator slows and comes to a stop. Then when we change directions, feeling lighter than normal, and then as the elevator slows and comes to a stop, he's going to feel heavier at the bottom. Take a look at that acceleration versus time graph as it's going on. When it's down here, we're feeling lighter. And then normal when there's no acceleration, and then lighter because it's negative acceleration, and then heavier when it's positive acceleration. Elevator has a downward acceleration at the top, moving up, getting slower, or moving down and getting faster. Downward acceleration means the upward normal force is weaker than the downward weight force, so the person feels lighter than they're used to. The elevator has an upward acceleration at the bottom, moving up, getting faster, or moving down, going slower. Upward acceleration means the upward normal force is stronger than the downward weight force, so the person feels heavier.